Hey, this is Mr. J here. Let's go through two examples of using similar triangles to find missing sides of real-world applications. So in this example here, it looks like we've got a small triangle and a big triangle. We know that they're similar because you've got this right angle here is this right angle right here is equal to that right angle right there is congruent. We've got this angle marked congruent there as well. So what we've got going on here is it looks like that we've got the sun shines over the top of this tree, and this ray of light here creates this shadow. And so in this real world example, we're trying to use the shadow side as well as this other triangle here on these two sides to find the missing height of the tree. All right, so the easiest way to work this out is to take these two horizontal sides and create a scale factor that's going to stretch that 3 feet to a much taller height of the tree. So we're going to do a big over small. We're going to set that equal to the 24 over 2, and then we're simply going to multiply that times the 3, right? So what do we get there? That's 12 times 3 is equal to 36 feet, right? So there's our answer for the first one. Real world scenario, tree creating a shadow. We're using the length of that shadow along with this similar triangle over here to solve for a missing height of the tree. Right. Okay, in this second example, what we've got here appears to be a flashlight that is shining rays of light past, let's say it's a circular disc. It creates this bigger shadow on the wall, and that's what we want to solve for x. Okay, so we've got this in green, we've got this smaller, what appears to be an isosceles triangle, inside of this bigger isosceles triangle. Okay, oops. And then we know that we've got right angles here because this should be parallel to that. So we got right angles here, so we got right triangles. Okay, so we got right triangles there. And so what we really need to know is we need to know the information about this altitude here, right? So there's the altitude of the small triangle, and then there's the full altitude of the big triangle. Okay, so let's start out by finding this altitude right here of the small triangle. Okay, so we've been given a leg and we've been given the hypotenuse. So let's set up our modified Pythagorean theorem where c squared is equal to a squared plus b squared. So I know that, and I know one of these legs. So I'm just going to go straight in here and I'm going to do 5 squared minus the 3 squared. Okay, and so that's 25 minus 9 is equal to 16, and then of course I would take the square root of that like you would do at the end there. Okay, so it looks like we've got 4 here. So that length right there is 4. All right, so looks like that we're stretching the smaller disc, which appears to be, with that going right through the middle, that right there should be 3 inches. So the entire length of the smaller disc that is creating the shadow is 6 inches. All right, so we're stretching from 6 inches to a shadow that's bigger, so let's do a big over small. All right, so let's start out with the altitude. The entire length of the altitude of the big isosceles triangle appears to be 4 plus 12, right? So that's going to be 16. All right, so we've got this small altitude, which is going to be 4, so that tells us the scale factor right there is 4 when we do the division. And so let's multiply that times the 6, which is the disk. So we have to find the length of the shadow. So we have 4 times 6 is equal to 24 inches. So it appears that the length of the shadow is 24 inches based on the fact that we've got this scale factor of 4. Thanks.